Ladies and gentlemen, we're going to have an interesting talk about bugs in the blockchain brought to you by Louis and Gabi.
Hello, everybody. Yeah, thanks a lot for coming. It's still early. I'm glad everyone could make it. So our talk is called "Don't Panic: Bytes, Blocks, Bugs." And I'm Louis. I'm a security researcher. I've been working on this topic of finding bugs in blockchain for almost 2 years now. And I've also focused a lot in the past 2 years on tool development around our audit efforts.
Yeah. Good morning, everyone. I'm Gabi. Thank you for making it this morning. We know it can be a bit difficult after like 3-4 days of camp. I'm a security researcher, and currently I'm focusing on finding bugs in blockchains.
All right, so blockchains. They've been in the news quite a lot in the past couple of years. Not always for the good reasons. A lot of time it's because a lot of money gets stolen from somewhere or a lot of money gets lost. And it seems like a lot of attackers have a big advantage in the field. So as security researchers, we're kind of trying to be proactive, and we want to share with you today the knowledge of how we find bugs and which kind of bugs we find in those blockchain systems, so that everybody can learn from our work. So today we'll be going through 5 common types of bugs that we find in a specific framework that we'll talk about a bit later, and how to find those bugs. So this is kind of a small shocker bug that I want to quickly present to show you how important this auditing process can be for blockchain systems. So this was an Ethereum project that, because of this one line, basically crumbled on itself. This wasn't a hack per se. It wasn't like an attacker stealing money or something. It was just one line that made the whole project collapse on itself, and everybody that had put money into the project just basically lost everything. And the code was brand new, unaudited. The developers said, "Guys, please don't put your money in yet. We want to, finish up stuff," and people still put way too much money in there and basically lost everything. So yeah, just because of this one line, which is an overflow in the multiplication, that made it so that the developers, or I mean the community, lost control over the governance of the contract, and yeah, made it impossible to recover. Everybody lost funds. So as an attacker, what can you gain from blockchains? The first obvious way is just like stealing funds. If you are able to find some kind of a bug that allows you to steal funds from one address or a contract or whatever, you can just take those funds or these assets, put them on an exchange, exchange them for real money, and then walk away with your gains. Then the other way that we'll also be looking at today is that if you are able to mess with the availability of the chain, or make it mess with people's expectations of what the project should act like, then you can diminish the overall value of the chain. And if, as an attacker, you knew that in advance and you shorted the token in some way, then you can also gain some money this way, and this actually might be even harder to trace than the first way. There are a few other ways an attacker can gain money from attacking blockchains. We were not going to cover them today, but these include, for example, DeFi attacks, so decentralized finance, also, and attacking the underlying IT infrastructure, which can happen, of course. Social engineering, which has happened a lot in the past couple of years, and yeah, also just rug pull from the developers, financial scams. So yeah, we'll first be giving you an intro of these blockchains. Then we'll explain the 5 types of bugs that we wanted to outline to you today. These are not exhaustive. It's just 5 types that we find interesting and that we think are that you might enjoy learning about. We'll be showing you examples of real-world bugs that we found in the past couple of years, and then we'll show you how we can use fuzzing to actually find those bugs proactively and effectively. And yeah, go ahead, Gabi.
Thank you. So today we are going to focus on the latest blockchain technology, which is called the 3rd generation. But let's just quickly go back and check the other 2 ones. So the 1st generation is the Bitcoin. Basically, you all know it. It allows you to transfer assets from one party to the other. And compared with the other 2 generations, it has quite a simplicity, let's say. Also, currently there are not too many bugs that are being found in Bitcoin, and probably this is also because it's quite simple, let's say. Then the 2nd generation came out, and it introduced the concept of smart contracts. So basically now you are able to execute code on top of the blockchain. So you can write your contracts, your agreements, and they are going to be executed and stored in the blockchain. This also introduces the possibility of creating business logic. So basically companies actually started to develop themselves on the blockchain. Now the idea with the 2nd generation is that you have the smart contracts that are all being run on the same core. The 3rd generation comes out and says, okay, instead of having one core and a bunch of smart contracts, let's empower the developers to actually create their own blockchains so they can define the core themselves. And in this case, basically, we are going to end up with a bunch of smaller blockchains, each one of them targeting a specific use case. But now the question is, how do you make all of them communicate with each other and actually being an ecosystem? So the 3rd generation also introduces the interoperability, so all of these smaller blockchains can communicate with each other. Also, there are multiple frameworks that are built on the 3rd generation, and today we are actually going to focus on one of them, and it is called Substrate, and we are going to focus on it because basically we have our experience is the most with Substrate, so it's just easier for us to give you real-life examples of bugs and attacks, but all the things that we are going to present you here can be applied to other blockchains as well. The team that is building Substrate, they are also running 2 blockchains, Polkadot and Kusama, and probably a lot of you know more about Polkadot than the name of Substrate, let's say. But besides these 2 projects, in the ecosystem there are another 150 projects that are using the framework. So basically now we are faced with the research question on how do we actually make sure that all these 150 projects are actually secure, and how can we automate this in a way, because at this scale basically you need to automate as much as possible. Let's have a quick look at the architecture of Substrate. It has all the usual components like peer-to-peer networking, RPC, telemetry, and so on. But today we are going to focus on the WASM runtime, which basically it's the core of the blockchain. In Substrate, basically this runtime it's being built using modules. These modules in Substrate are being called pallets. Throughout the presentation, we're gonna try to use the term modules so we don't introduce too many new terms for you. And the idea is that basically when a developer wants to create a blockchain, they can either use, like cherry pick actually, a bunch of these pallets that are already provided by Substrate. So you can choose your consensus, you can choose if your blockchain will be able to run smart contracts or not, randomness, and so on. And on top of this, you are going to come up with your own modules that are going to bring basically your own business logic. Okay, so now let's just quickly look actually. I suppose all of you came here for seeing the attacks and the bugs, so let's just dive into that.
Yeah, let's go. So we'll be looking at 5 major classes of bugs that we've defined today. So attack type A, bug type A would be like wrongly priced transactions. So if a transaction doesn't have the right gas associated with it, then maybe we can exhaust the resources of the chain, causing some kind of a denial of service. Bug type B is we're going to look at logic bugs and unsafe arithmetic to manipulate the actual program flow. This will hinder, of course, the integrity of the chain because you might be able to tweak a number that you weren't supposed to be able to tweak. But as we'll see, it can also impact availability because those numbers might be associated with availability, the numbers that you tweak. Bug type C will be looking at the reachable panics. This is a very Rust-specific bug type that we'll be taking a look at. And bug type D encourage usage of standard patterns, so basically misconfigurations in the blockchain code, because we said that there were quite a lot of things you could import, and if you import stuff with the wrong configuration, then you might be vulnerable to any kind of misbehavior. And bug type E will be looking at storage bloating, so that's like inserting a whole lot of data into the blockchain storage and cause some availability mishaps. So first, wrongly priced transactions. The idea here is that operations on those substrate-based blockchains are benchmarked, and then the benchmark time basically is translated into a gas fee that you have to pay in order to run the operation on the network. So whenever I want to run an operation A, it has an associated gas fee of N, and I have to pay N in order to run A. And if A was not well benchmarked, then I might be able to spam it, and then the node that tries to run the whole block might just like not finish running it in time because it estimated how much it would need to how much time it would need beforehand, and if it wrongly estimated because the benchmark was wrong, then you might be able to make it basically it's not a timeout, but at least you're going to slow the whole thing down and maybe cause some people to be blamed for slowing it down that were not you. So I'm going to talk about a very cool bug that is related to what I just mentioned, but not exactly what I just mentioned. Because this bug that we found, our fuzzer found it actually, it applies not during the running of the actual operation, but during the computing of the weight of the gas cost of the function. So you can see on the left, this is the gas computation of an operation that's called Pseudo As, and this Pseudo As takes as an argument another operation to run as pseudo and to run as root. And this, of course, this Pseudo As can only be run by, for example, a governance call. It cannot be run just by anybody. It's also used for development, for debugging. But in real life chains, it also exists, and it can only be used by governance, basically. But this, the computation of the gas cost of a Pseudo As has to take into account the computation of the gas cost of the child operation. And if you look at the way that the computation is done, it calls the child computation function twice. And that means that you can actually get an exponential number of function calls just by nesting those Pseudo As calls or any other call that was vulnerable to this, and there were a few. You can nest them, and then, for example, if you nest them 41 times, you get more than 1 trillion leaves. And basically, the node that is going to try to run that, it's not even going to go to the logic of the code at any point. So it's not even going to have time to check at any point that you're actually who you're claiming to be. So you can call this as just anybody. And it's just going to time out and completely hang during the weight computation. So yeah, this was a very cool bug that we found a couple of years ago.
Okay, so if we are going to have a criminal that is looking more into how to manipulate the flow of the program, there are 2 ways of doing this. The first one is taking advantage of the usage of unsafe arithmetic. And as an example, here it's part of a function that can be called by any user. Now this function takes a few arguments, one of them being a vector of messages. These messages have to be processed by the blockchain, so before processing them, the blockchain is going to calculate the weight of each message, then sum all of the weights up, and then it will just check, hey, is the sum of the weight smaller than the maximum weight that I'm supposed to be able to calculate, and in case if it's not, it will return an error. Now, the problem in this code is that the sum function is being used to calculate this weight, and the sum function is not using safe arithmetic, so it can actually overflow. So in this case, an attacker can come in and actually execute this function with a large vector. So basically, when the sum is going to be called, the weight calculation is going to overflow and wrap around, and in the end, we are going to end up with a very small weight for actually a super large amount of work to be done. So the node will consider, hey, I can actually execute this in the amount of time that I'm supposed to, but actually it won't be able and it will time out. Now, in order to fix the previous vulnerability, you just consider, hey, I will just use safe arithmetic as the checked function, but that's not always fixing the issue, because when you use safe arithmetic, it will actually return you an option, so you have to properly handle the error that is going to be returned in case of an overflow. In here, the developers are using the checked functions, which is fine, but they are not properly handling the case of an overflow. So the function that can be called here by a criminal allows you to control the begin end of the message count parameters. So basically, if you are going to call this function with an end value of U64 max and the other two ones as 0, in the end, the blockchain will try to allocate a vector with the capacity of U64 max, which of course is going to crash the node, and it will end up with availability issues in the blockchain. Now, looking into the logic bugs, in here we have an example of a blockchain that basically a user comes in and says, the user actually has to validate their identity. So a user will come in and say, hey, this is my identity. Then a registrar will pick up the request from the user, will check it, and it will say, yes, your identity is legit or not. Now, what the registrar will specifically say, yes, this user provided a valid identity, but it won't say that it provided this specific identity. It will just say that the user provided an identity, right? So in the end, what a hacker can do is submit a request for a legit identity, then monitor the network and see when the registrar actually comes in and says, yes, this identity is legit, and execute another transaction very quickly with a spoofed identity and a higher tip. So basically, in the same block, the hacker will change their identity with a spoofed one, and the registrar will still consider that identity as being valid.
All right. Now moving on to reachable panic for availability issues. Now this is these reachable panics. It's a bit more complicated now. Like there are some changes in the code that make it not so clear cut. The nodes are not just gonna panic in most situations, but sometimes they do, and we wanna include it for. Because we think it's still very interesting. So in Rust, because all of these blockchains and the code snippets you've seen so far are coded in Rust, if you can't handle some kind of a result that you did, you have the option to unwrap the result, and then if the result is valid, then the program flow continues. If the result is invalid, that you decided as a programmer that the state of the program was not recoverable, and you just panic. And this is very useful in a development scenario because you just don't care about if the result is going to be there or not, and you can just put unwrap everywhere as a developer, and it's going to speed up your development, and you can come back to those unwraps later and maybe add some management of these edge cases. But sometimes those unwraps get forgotten in the code, and this was a situation where in some kind of a decentralized exchange there was a conversion function that was doing a checked multiplication, and the programmers had forgotten to handle the case where the checked multiplication was returning a non-valid result, like if it was overflowing, and it was just unwrapping, and then basically the whole node might just go boom and have to restart its process. Yeah, so that's these are perfect targets for the fuzzers, by the way. That will be showing up in a bit.
Okay, so in the beginning of the presentation, I was telling you that you can create your own runtime just by cherry-picking some modules that are already provided by the framework. But now, when you actually create and import these modules, you are also supposed to set some parameters for these modules. And there might be a bug in there, actually, if you don't set these parameters correctly. In Substrate, each account has actually, it's represented by a structure, and inside we're gonna find the balance of the user, some internal counters, and you can also enhance these structures with more parameters that are specific to your project. So basically, each account is going to take some space in the storage of the blockchain. Now the idea is that you should not be able to store such data and have such an account if there is no token in your account. And for this, there is a parameter that is called Existential Deposit. And basically, this parameter will say, hey, this account is allowed to exist as long as there is at least an X amount of tokens in that account. Now, it often happens that this existential deposit is being set to 0 or to a small value, such as during the development process, it's just easier for the developers to test everything. But if this goes into production, then a criminal will be able to come in and create a super large amount of accounts for a very small fee, or also for free. So basically, in the end, bloating the storage of the blockchain and making it run slower and slower in the long run.
All right, now we're going to move to storage bloating as a class of issues itself. I mean, Gabby already explained most of the issue already. The issue with storage bloating is that if you, as a random person, try to join the network in the future with a full node or something, if you have to download terabytes of data to actually make the node run, it's not going to be easy. It's not going to, it's not going to make it universally available to everybody if you have to download terabytes of data. So yeah, so we take this class of bugs seriously when we review a project. If the fee for creating some kind of storage item is way too low, then we report that to the teams. And here, in this specific situation, there was a module under construction that was handling bridges to other chains, and it was not ready yet, but they wanted still to publish the code without the actual bridges part implemented. So they just had the registration of bridges open to the public so that you could pre-register your bridges with the identifications you wanted, and then in the future you would be able to send out those to create those bridges for real. The thing is, here they had set the required state for the amount that you needed for creating a bridge way too low. Like, this is 1 million, and it basically means 1 million of like thousands of a fractions of a fraction of a millionth of a cent. So in the end, it's like almost nothing in euro terms. So you could just register spam this bridge registering, and it would allocate quite a big amount of data on the chain. But most importantly, in the future, when those bridges would actually be implemented for real, this amount of data would actually probably also go up. So yeah, this is a classic storage bloating issue.
Okay, so now that you are aware of what type of bugs are we looking for in the blockchain, you might be wondering, how can I actually start finding some of this? And there are at least 3 techniques that you can use. 2 of them are automated, and the third one, it's the manual code review. We're going to start with the third one. So basically, if you are already doing some manual code review, it should be quite easy for you to move to the blockchain world. But you have to keep in mind that a different threat model will be applied here. Because, for example, in a Android application, let's say, if you have a crash, okay, that's fine. The app is going to crash. You just open it again. But in a blockchain, if you have a crash, that might actually be a critical vulnerability in the end. So for the manual code review, you just need to change a bit the threat modeling and look for different stuff. Then, keeping in mind the 5 classes of bugs that we've showed, you are kind of on a good track to actually be able to start finding these bugs as well. Mostly using fuzzing, and for this we are also going to give you a demo about fuzzing. Mostly we are finding a lot of bugs with static analysis and fuzzing. Mostly all of them, I would say, but of course the manual review is all the time complementary.
All right, so very quickly, what's fuzzing and how do we apply it to these blockchain projects? Fuzzing is when you take a program and you feed it a whole bunch of inputs and you wait for any kind of misbehavior to happen or something that you've aligned to trigger. And in this situation, the program is the blockchain runtime itself, so the part of the blockchain that executes transactions one after the other and that interacts with the storage and everything else. And our fuzzers are coverage-guided fuzzers, and they're going to look at the code coverage inside of the blockchain application to see what's interesting and what's not. And yeah, it's going to find really complex stuff quite fast, and that it really works very well in this situation. So to make it really quick, the fuzzer is going to have a bunch of potential inputs. It's maybe going to apply some mutations to it. Then the fuzzing harness will decode these inputs. So like take one input and split it into a few transactions, decode those transactions, and then run them one after the other, maybe skipping a few blocks here and there for timing purposes. And then yeah, the target is gonna just run the program, and if we find some kind of an overflow, some kind of a crash, some kind of a timeout, or any other pre-programmed values that we've set to trigger, yeah, it's gonna report a crash, and we'll take a manual look. All right, now time for the demo. So we launched a fuzzer a bit before the talk. We hope it found the crash that we wanted it to find. Just to show you, this is the interesting one interesting part of the runtime code that we're gonna fuzz. This is the template runtime, so like the one that you're supposed to start with if you want a normal substrate stack, and these define the different modules that you're going to have in your chain. So the interesting one here is the template module, which is, as it says, a template module, which is defined right there. And in this template module, you have 2 calls. The first one is called do something. It's going to take a U32 as an input, and it's going to put it into a storage item. The second one, it's called cause error. It's to show you how an operation can cause an error and return an error in a safe way. And it's going to take the value that you put into storage. If it was nothing, then it's going to return an error. If it was something, then it's going to increment it. Now, the original code for this is a checked addition. And the the code that we actually we replaced it with to find a crash is just new is equal to old plus 1. So unchecked math, the classic, classic mistake that we see over and over again, and then it puts that new value into storage. Now, let's look at our fuzzer for a bit. It's like 300 lines of code. It's open source. I'll show you the the repo in a bit. And yeah, you basically decode stuff and then run the. Let me show you the running of it. You just run the extrinsic here, and the rest is basically stuff that we've added over the years to make sure that to make sure the situation is perfect for our fuzzers to find a crash. So let's look at how the fuzzers has been doing. It has found a crash. Perfect. We are going to be able to show it to you then. And this crash hopefully is running the do something extrinsic first, the do something operation with U32 max, and then cause error. And this should crash the chain because there was an overflow. Oh yeah, one thing I forgot to mention is that the fuzzer has some checks enabled. For example, this overflow check, because in a real-world scenario, like the blockchain would just make the value overflow and you wouldn't see anything except for the value that has overflowed. But in our situation, we want to catch those. So the fuzzer will actually catch those overflows as crashes. All right, so this is Ziggy. It's our in-house manager of fuzzers. It launches an AFL instance, or a few. I think there are like 40 of them on this server, and also HongFuzz in parallel. And then they share corpus so that they can learn from each other. And yeah, let's try to run the crash that we found. All right, what does it say? It says that it tried to do something with a value that looks very much like U32 max, and then it ran cause error, and yeah, there it crashed to attempt to add with overflow. So we found the bug that we had planted there in our template, and this is a very easy or quite easy way to find a lot of bugs in many blockchain systems. Now, to show you the impact that this have had, first. The harness itself is open source. Please go check it out in this repo. The Ziggy, the tool that you saw that we use to manage the fuzzers, is also open source, and you can find it there. And now back to Gabi.
Okay, so now you are aware of what kind of bugs we can find them. Louis just showed you that the fuzzer that we are using, it's also open source. So with these two, you are kind of on a good track to actually start and finding bugs by yourself. And in the past 1.5 years, we analyzed 45 projects in the ecosystem, and most of the bugs that we found were actually found in a semi-automated way. Most of them using the fuzzer harness that we've showed before. So. The idea is that you can actually start and playing around with this. You can contribute to the ecosystem, and you can do this out of curiosity, of course, or you can even look into some of the projects in the ecosystem that are running bug bounties programs. So in the end, while we, like in the past 1.5 years, 2 years, we developed our tooling all the time in order to be able to automate as much as possible and cover as many projects as we could. But of course, as I said in the beginning, there are over 150 projects in the ecosystem. We covered only 45 so far, so we are kind of aware that in order to have an impact, we need the help of the community for this, and this is why we also open sourced the fuzzer, and we encourage you to start playing around with that. You can consider it a new game, a new puzzle, whatever gets you excited about it. Also, as I was saying about the manual code review, the ecosystem itself kind of needs a different threat modeling than the usual security reviews that we are doing. So the entire ecosystem would benefit if both the developers and the security researchers will start collaborate more and share this new threat modeling with everyone. So with that being said, thank you very much for making it to our talk this morning. We are waiting for your PRs, comments, or anything on the open source fuzzer. Thank you.
We still have some time for a few questions. If you have a question, please line up at the microphone over there. Signal Angel, is the internet already awake? No, the internet is still asleep. They do not have any questions. Anyone else from the audience with a question?
I didn't understand the incentives for paying $25,000 to use 1 gigabyte of storage on the blockchain. Like, what's the attacker model? Who would want to do that?
That's a good point. Yeah, I heard other blockchains right there. I guess you have an incentive to make your competitor project as hard to get into as possible. And it is a lot of money, this 25K for 1 gigabyte. But if you compare it to other blockchains, for example, Ethereum, you would need to pay like tens of millions of dollars to actually put a gigabyte on that blockchain. Which then the idea is that you make it harder for other people to get into the ecosystem. And I mean, this issue was probably low or maybe medium severity, probably low. But potentially you could find something that scales even better, and where you can actually go hard on the storage.
So don't like asynchronous programming paradigms and things like this usually say that you should embrace panics and shouldn't like. Isn't it a major failure to try and exclude all the panics?
Yeah, that's an interesting idea. I guess in that scenario, some nodes are incentivized to publish blocks because they will get some reward out of it. And if an attacker can make them unable to produce them, they might even get punished for it. So. Yeah, I guess on a theoretical way, I agree, but the incentives are aligned so that an attacker wanting to make a node panic will actually, cause a bit of mayhem in the process.
Thank you for your talk. Let's give another round of applause to Louis and Gabi.